Okay. Thank you for coming. I'm lighting up these lights with my foot. So today is the last time we talk about this harmonic oscillator. So I want to talk about the irreversibility within this model and see how it shows in the infinite size limit, and introduces the concept of self-energy and virtual particles in this context. But first, are there any questions regarding last time? Okay. So first, I will spend a few minutes to go back to this susceptibility, chi of r here. So x of r is something like times the driving force, and that's something I call a susceptibility, and it's a retarded susceptibility. So what's different from what you have seen before is that now I put omega plus I eta. This is the retarded, so I don't need to put omega plus I eta. It's implied in the retarded limit, plus omega squared. So why do I do this? I do this because if there's no damping, for example, so if suppose that gamma is 0, then you see that you need the poles to be in the correct in the lower half plane, and that's the way they will be in the lower half plane. So another way to see this is that if I write the susceptibility chi of r of omega as integral t omega prime over pi of chi double prime of omega prime divided by omega prime minus omega plus I eta. I argued last time that this is the definition of the retarded function, and we need to, well, what is implicit is that we need to take the limit eta goes to 0. So you see, if I have a harmonic oscillator that is not damped, then there will be the chi double prime, which is related to absorption, will have a delta function, will be a delta function. So, so if you replace this by a delta function, you see that you have omega plus I eta. So everywhere you have omega, you need to add plus I eta. So if it doesn't make any, so here, when I have some damping, I can immediately take the limit of eta goes to 0. This is a continuous function. But here, with a discrete set of oscillator, you will see that it's important to have omega plus I eta everywhere.
Does the argument of the force should also take this I eta?
Yes, good point. Yes.
Oh, okay.
So here it's the, if you want, you can think of it as the retarded force. So I don't need to put it, but yeah, in general, I definitely need to put the omega plus I eta. An excellent point. So I'll put retarded so that, in fact, that will be that will be important for the coupling to the electromagnetic field. So it's not a trivial question. I should have pointed it out. Okay, so okay. Now, what are the properties of this function? You have already, well, I have not done the derivation, but I hope you have looked at it. There's omega times the chi double prime of omega is positive. So that's a way to have a positive dissipation. The other thing is that the poles of this function are the collective modes, or if you want, this is the response. So if the force goes to 0, then you can have a response with a 0 force because you have poles here. So this will come back very often also, that poles of this response functions are collective mode, if you want. They are related to response. Then the other thing is that the double prime of omega is odd. So gamma can be a constant if you want. Take the case where gamma is a constant. When you take the imaginary part, then it's gamma. It's I is here. So if you multiply by the complex conjugate numerator denominator, you see that double prime is odd. That's a general property for some certain types of correlation function. Now, the other thing is that if omega goes to infinity, then this becomes negligible and this becomes negligible as well. So in the infinite frequency limit, it's inertia that dominates. So it's the mass that comes in. And we will see that gamma goes to 0 at infinity. So that's another important property. Now, the other thing is the fluctuation dissipation theorem, which I will not prove, and is not done correctly in the notes for the, or at least it's very clumsy in the notes for the classical case. But in the what we mean by fluctuation dissipation is that the Fourier transform of this quantity, which is the fluctuations. So let me write this as let's write the Fourier transform of this okay, as S x of omega. It's equal to 2 kBt over omega times chi double prime of omega. That's so the fluctuations here are related to the response. And in the classical case, it's a little bit it's not so trivial. It's a little bit, the derivation is a little bit clumsy. But in the quantum case, it's very easy. So we will restrict ourselves to the quantum case and we will recover the classical limit that I just pointed out. So any questions? Okay. So now we go back to our Caldeira-Leggett example. So what I have, so remember that we have the mass that we are interested in. And this is just a model for the bat. It's a model for these other particles that are doing the damping. And so this is a spring constant K. This spring here I call K double prime. And the reason is just that it's sort of a coupling constant between this and the bat. And then K prime is, these K prime are just properties of the bat. And you have the masses here and the displacements. And you write the potential energy. So that's kx squared. Then we have K double prime x minus U1. So x minus U1 squared, that's the potential energy. The dashed line is like the equilibrium position. And then all the other ones are K prime, U1 minus U2. And okay, so now I said, to simplify the discussion, I will take all the masses equal to 1. In the notes, I've taken care of the masses, and it's just a complication that makes the algebra a little bit more difficult. But the message can be obtained even if I take the mass, all the masses equal to 1. So this is what I do now. I take all the masses equal to 1, the big one and all the other ones. Okay. So now the force here is the minus the derivative of v, which is partial derivative of v with respect to x, right? So I have minus kx, and then I have minus k double prime x minus u1, and then I have some force on this mass. You can imagine, for example, that this one is charged and the other ones are not, and you're applying some electric field. Now, the equation of motion now for u1, there's it comes here. I can sort of put it the other direction because it's square, and then it's easy. If you take the derivative minus the derivative, you get u1 minus x, and then u1 minus u2, and you keep going. Okay, so now I will take the Fourier transforms of this, and so the second derivative with respect to time becomes minus the square of the frequency. But for frequency, I need omega plus I eta everywhere. So I will call this minus z squared, and I'll take omega plus I eta at the end. Is that clear? Okay. Then I put this on that side, so I get k, and this on that side, so it's plus k double prime. And I have x here, and it's equal to f. But I need this here. So this one here is also on now it has an opposite sign, because here it's positive. So when I put it on the other side, it's negative. So I get minus k double prime that goes with the u1 here. And then I have 0, right? I'm not coupled to the other ones. 0. So now if I look at u1, I have k double prime u1 that in the diagonal piece. So here I have minus z squared, and then k double prime plus k double prime. And then I put this on the side, so plus k prime. And now the coupling to x, again, it's on the other side, so it's minus k double prime. So the matrix is symmetric, you're not surprised. And here, how do I couple with the u2? U2, here I have a plus. When I put on the other side, is minus. So I get minus k prime, and then 0, and then 0, and minus k prime, and some element here on the diagonal, and you keep going, okay? I will, it is a band diagonal matrix. You have k prime here. So the structure of this matrix is we have this element here that I will call, I want to solve for x, okay? So this element I will call, I will call d0 minus 1, okay? And it's a function of z. I will spare this. And now this here is a vector that I will write as v. And here is the transpose of that vector that I will write as v transpose. And here I have a matrix that I will write as a d, so it's like a propagator, d for the bat to the minus 1. And then I have, whoops. this part of the, I don't know if it's only my pen. Okay. Then I have X and I have U, and it's equal to the force F. So you have to think of U as a vector. This is the vector U1 up to UN, and D minus 1 is this, this matrix. And what is D minus 1B? D minus 1B is minus Z squared plus a matrix K that is symmetric. Okay, the matrix K is this on the diagonal, and these elements in the off diagonal. So this is a real symmetric matrix. Okay, so now it's easy to solve because the this vector here, F, is really F and 0. So we will solve for U using this line here. So U will be written as a function of X. Whoops. The board is moving. You still see everything?
Yeah, it's all right.
Okay. Okay, to solve this, we first use this line. So to solve this line, you see that we get that D minus 1 B times U is equal to V transpose minus V transpose times X. So U is equal to minus dB times V transpose times X. And now we can substitute in this line, and we get that running out of juice here, I think. We get that D0 minus 1 X plus V times U, and U is this. So it's minus V times dB times V transpose times X is equal to the force. Okay, so we basically found the solution because we can easily invert that the X is equal to D0 minus 1 minus V dB V transpose to the minus 1 times F. So this this thing in mathematics is called Schur's complement, but we will never use that again as use that name again, but it's useful to know. And this here, and when we do the Anderson impurity model, this will be the hybridization function, this kind of combination. So you see there's a coupling constant here between the bat and the mass that comes in here, V, and then there's the bat that is there. So the poles of this quantity here, which are the eigenmodes, are where this object is equal to 0. So let me work on it a little bit to express this in terms of eigenmodes. So we can diagonalize this very quickly, because this is K is a real symmetric matrix, right? So dB we can write like this. So dB we can write like some matrix O times minus Z square plus a diagonal matrix times O transpose. Okay? So it means that this I can rewrite using this. And that will allow me to illustrate where the poles are. Are you okay? No question?
I'm not sure why we could do this.
Because K is a real symmetric matrix. So it is diagonalized by an orthogonal transformation. So O times O transpose, O times O transpose is the identity. So normally you have, if you want, I have that K is equal to O times the diagonal matrix times O transpose, and O times O transpose is equal to the identity. Are you with me?
Yeah, I'm with you, but is O a matrix?
Yes, O is a matrix.
Oh, okay.
Right?
Okay, I get you now.
Okay, because this D is a matrix, and I'm sorry, this D minus 1B, there are too many B's here, is this matrix, which is not diagonal. It has these minus Z square on the diagonal, and then the rest is a real symmetric matrix. You see, you have minus K prime, and this continues this way. So a real symmetric matrix can be diagonalized by an orthogonal transformation. And that's what I did here. Okay. So it means that now now what I have here is V O. So V times O is still a vector because O is a square matrix. And so V times O is a vector. And then I have the diagonal matrix D. And then here I have O transpose times V transpose to the minus 1 equals F. Okay, so I'm almost finished. You're patient. I'm sorry it's taking so much time. But to find the poles, we just need to look at the zeros of this object, okay, because it's minus 1. So let me write this.
On the last line you wrote,
This, yes.
It's equal to F. It's not
No,
applied.
no. Times F.
Okay.
Sorry. Yes, we're just inverting this equation, you see. So now I will simplify the notation a little bit. And I said that V times O is a vector, okay? And that's another vector here. So I will write T and T transpose. Okay, so it's just a shorthand for this V times O. Okay, it's painful, but we're coming to the end. So a little bit of patience, and we will be happy. Okay, so So the inside here is equal to what? Is equal to minus z squared plus k prime. So that's this element. And then I have minus sum over the eigenmodes alpha, t of alpha, and this diagonal matrix is did I make a mistake here? D. It's okay, yeah. Okay, you have to remember that dB here is the inverse of this matrix. Because on the left-hand side, I had dB minus 1. When I found the U, I inverted this matrix here. So this, I'm looking at the inverse of this. So I have T alpha 1 over minus Z squared plus omega alpha square times T alpha. Yes. So this is this object. Now so the poles of this.
What is T alpha?
So T alpha is one of the elements. You see, T is a vector, and D is a diagonal matrix that is the inverse of this.
So it's T is the eigen vector of the.
Well, D is V times O times O is here. So here at the O was the eigenvectors, but now I multiply by V also. Okay. So that contains the coupling constants and the eigenvectors.
So it's T transposed that's equal to your the last two line you wrote.
Yes.
Okay.
Okay. Because this is vector, this is the inverse of this matrix, and that's T transpose. But that's a vector as well, so I just write it this way. Okay, and these are the eigenvalues. Okay. So here is the important point now. If we look at the poles of this propagator here, given by the zeros of this, and there's a discrete number of poles, right? Because here there will be, if there are n harmonic oscillators here, there will be n eigenvalues. Okay. So when I look at the solutions of this equal to 0, I can put everything on a common denominator. And you see that I will have a polynomial in Z squared that will be of order what? Of order 1, of order n.
N plus 1.
N plus 1, okay? You imagine that you put everything here on a common denominator. Then that's a polynomial. In the denominator here would be a polynomial of order n. And then you multiply that polynomial by this. And that's the polynomial of order n plus 1. So it means that if I look at the poles of this, right, which is like the poles of my susceptibility, then these poles in the complex plane so it's order n plus 1 in Z squared, but every time I have two solutions, right? I have with plus and minus. So the poles will be located infinitesimally below the real axis. 2, 3, 4, 5. 1, 2, 3, 4, 5. And I have when I have a pole with the positive value of the real part of omega, then I have one with the negative value of omega. So you have to think of this as the real part of Z and the imaginary part of Z. So let me rewrite this in a different way so that you see better what is happening. So 1 over minus Z square plus omega square alpha is equal to 1 over 2 omega alpha times 1 over minus Z square minus Z, sorry, plus omega alpha minus 1 over Z minus Z see, if I put on a common denominator here, I will have minus Z square. So I need a plus here. Minus Z square plus omega alpha square. That's this. And then I have I'm doing something wrong here. Sorry.
The sign in between is wrong, I'm pretty sure.
Yes. So I will do it this way. We'll give the same sign with Z and opposite signs with alpha. So that is minus 2 minus omega alpha, so that's minus 2 omega alpha. So that cancels the omega alpha. And here I get Z squared minus omega alpha squared. So I get this backwards. So I get rid of the minus sign. Okay, so I think I got this correctly now. So so you see what will happen is that if now instead I write if instead of this I write chi double prime of omega, okay? So I write chi double prime of omega on this axis, and I write omega here. So this omega is now real, and chi double prime is the imaginary part of the quantity. You see that the poles will be, as I said here, at omega alpha and minus omega alpha. And also what will happen is that they will have a different sign, because we said that chi double prime was odd. So it will have a different sign depending on if it's on the right or the left. So chi double prime of omega will be some function like this, a set of delta function. Okay. And it's anti-symmetric. Okay. So when I have a discrete set of modes here, if I get I give some force and I look at it evolving, then it will eventually, I mean, there can be incommensurate frequencies that will give me some problem. But in some sense, it's always coming back. It's reversible. you can, so if you have some Fourier series with a finite number of modes, you expand, it gives you a periodic function. Okay. Is that okay? So now, how do we go to the infinite size limit? So to go to the infinite size limit, what we will do is we take an infinite number of modes here. And I will not do the details of the calculation. It is in the notes. So I ask you to, it's part of what you need to do for this class to, when you hand out the notes, you can check the continuous limit. So in the continuous limit, what I do is I define a density of states, if you want, n, density of mode n of omega square, which will be equal to sum over alpha of t alpha square times delta of omega alpha square minus omega square. Okay, and I take t alpha to have I take an infinite number of modes. So this chain now becomes infinite. So the coupling to each mode will go like 1 over the number of sites here. I don't want to, if the chain is infinite, it doesn't mean that I have an infinite coupling to the chain. Okay. So I want to take this infinite size limit. This becomes an integral. So what happens when this becomes an integral? Instead of having a discrete set of poles here, I will have a branch cut. These poles all get together. And what's important is I take the infinite size limit before I take this eta goes to 0 limit here. So it's as if in the infinite size limit, this set of Lorentzian that become delta function when I take it, eta goes to 0. In the infinite size limit, they get close together. And the system is so big that I cannot resolve the energy difference between the eigenmodes. So I go from a Fourier series to a Fourier transform. So the infinite volume limit is what gives me irreversibility. What happens to this object? This object here now becomes some continuous function. For Caldeira prime. Is it okay? Now, if I do some approximation for this function here, I could, for example, I could decide that, oh, this looks like another Lorentzian. This looks like a Lorentzian, and this looks like another Lorentzian. Okay, that's an approximation. It's not the real thing. It's an approximation.
Sorry.
Yes.
I didn't understand from that line n as a function of omega squared. Yes, yes.
So what will happen here is that, you see, I can, this will become an integral now over n of omega squared. Okay. So if I can substitute, if I write, instead of this here, if I write minus integral d omega square of n of omega square times 1 over minus z square plus big omega square, then this is equal to this. Do you agree?
Yes.
So this is equal to this. But now, instead of saying that this is a set of discrete poles, I will replace this sum over alpha by an integral also, because I have an infinite number of modes. Okay, and now I can, and the t square here will be like 1 over, it will go like 1 over the number of modes, because you want to transform this discrete sum into an integral over omega alpha that will be finite. Okay, it's sort of a density of modes, if you want. So once I do this, then I mean the mathematics is worked out in the notes, but you can see already from here that what's happening is that instead of having a discrete set of poles one right next to each other, you get a branch cut. And this function here becomes a continuous function instead of just being a set of delta functions. So when I do this and this is just an exact. And now what I do is that on this line, I take the infinite size limit. And then in the infinite size limit, this becomes an integral. And that's just some function of omega squared that is continuous. And then instead of having all these peaks, you get some continuous functions.
Thanks.
Was it okay? Thank you for asking questions. Don't hesitate. So now this is exact. Okay, the poles form a branch cut now. The discontinuity is equal to this quantity, chi double prime. And this is this function. Now, if I decide to approximate this by some sort of Lorentzian, what will happen here, just one Lorentzian, what will happen is that I will have the poles here will move. I mean, a Lorentzian is just one pole, so it will move on far below the imaginary axis. So the exact function is as a branch cut here, but you can approximate it sometimes by a simple pole. So when you see these things that are very far from the real axis, like in this case, right? When we looked at the poles, when we had gamma here, the gamma was far below the real axis. But in reality, it's because it's an approximation to the function where the poles are really given by branch cuts. Now, another thing that you can see is that the damping gamma, which is related to this, here it was k double prime. The damping gamma that's related to this, you see gamma becomes a function of z. It becomes a function of frequency. And it goes to 0 in the infinite frequency limit. So that will be a very general result. It's important for some rules and so on. So in the infinite frequency limit, you recover free particles. Okay. Okay, now what about what do I mean by self-energy in this context? Okay, let's start with the let's start with this object that I will rewrite as this. So one over m times minus omega plus I eta square. And this I will write as, this is just a definition now, 2 omega 0 pi retarded of omega plus omega 0 square. This notation comes from studying phonons. But okay, this is just the definition for this. Now imagine that I have a scheme to do perturbation theory for this propagator. And I want to do perturbation theory in powers of this coupling constant here, K double prime. Okay. So K double prime comes in this this quantity. It's the coupling constant to this. So if I'm interested in the second order in K double prime, the result that I will get will be I don't have much time here, so I'm sort of perhaps cutting corners, but you will see that it will have a structure like this. D0, where D0 is the non-interacting propagator. So D0 D0 is 1 over m times minus omega plus I eta square plus omega 0 square. So if I define D0 like this, when I do power series, I will get D0 plus D0 times
it's becoming, the lines are becoming
too thin.
yeah.
Okay. This you can read. Can you read
Well,
it?
it's on the limit of what we can read.
Leading a limit of readability. Okay.
Yeah.
So let me move to red. So I assume you can read this. So you get the D0. Is it okay now?
It's much better.
Plus D0 times m omega 0 pi retarded times D0. So it's a minus sign. I'm just doing power series expansion. Minus. And then I continue. Okay. So I get higher and higher order. And then if I go to higher order, yes, I have to not only, this coupling constant, but it comes in, this and there, and to fourth order, it becomes a real mess. But my point is that if I can do a power series expansion, I should not do it on the propagator itself. I should do it on this object. Because why? Because the poles are given by this. You see, if I look at the poles of this, I have this pole that I expect, but here I have the square of that thing, right? And that doesn't make any sense according to our exact results there. So this, what you do when you do power series in D0, you get the first term you get is this. But then you say, okay, I'm going to go to higher orders. And I know that it has to resum this way. So this object is called the irreducible self-energy. So why is that? It's just because if I represent this by drawings, okay, so this D0 is this line, and then I get minus this line times a blob, which is this object, times this line. And then let me write it out. Let me put the signs in this mess here. Then the next term will be this times this times this times this. Okay, I'm just doing a geometric series here. So I'm expanding 1 plus x in the Taylor series in some sense. So when I expand the propagator directly, I get this plus this, okay? And then what I have to do is to say, okay, this object here that I computed to second order in the coupling constant, I don't need to go to all these orders. I can already resum it like this. So, so if I write that the result here is something plus something times this, okay? So here I will define.
Just, I'm lost. I'm lost since the moment we started to speak about the creating a series of power.
Yes.
And are those Feynman diagram or
Yes,
something
eventually
else?
they would be Feynman diagrams, but for now they're just I'm just drawing. Okay, I'm representing D0 here by this wiggly line.
Okay.
Okay.
Yeah.
And the real D is this. I mean, it has this denominator here. So the real D, let me rewrite it with. Oops, I have. You have to stop now. I'm sorry, but we have some color here. This is the real D. I mean, the one that is this object here, and it's equal to this here. And this will be, this object is called that I put here in the denominator is called the irreducible self-energy, because if I look at higher order, you see that these, if I call these self-energies as well, then you see I can cut this in two by cutting one of these propagator lines. So this guy is called the irreducible because of that. Because if I do this and I call everything here that the full series here, if I call it the self-energy, then this one here is the irreducible one. It goes directly in the denominator. We'll see this in other contexts, but it's in reality it's not more complicated than this. It's just related to the fact that if you do a power series expansion for the propagator, which is what we will do, then what you get is some infinite series like this, and you should always resum it to put it in the denominator, because that's what makes sense here. Otherwise, you see, you get the square of these poles there. And the thing that you put there is called the irreducible self-energy. So you see here, the power series for the propagator. Let's say this is of order k double prime square. You get k double prime square, k double prime 4, k double prime 6, etc., etc. But it's much better to put it in the denominator and expand this in powers of k double prime. Why? Because this thing here, you can hide your ignorance there. You can do some approximation where you can just replace this, for example, by a damping constant in some cases where you cannot do more detailed calculation. So is this okay?
Well, I'm still kind of lost, but I think I have to read a bunch more before I'll get it. So I'll come back to
so
you
I'll
if
let you read the notes, do the calculations and ask me questions, okay? Next time. I mean, that's the idea. So what do I want to say about virtual particles? I don't have much time. In fact, I don't have any time. But you can, I will tell you next time. But what is a particle in quantum mechanics? So if I have the harmonic oscillator, when I have a transition between two states, let's say the ground state and the first excited state, I see that I have absorbed a phonon. Okay. So that's a particle. I can have one phonon, two phonon, three phonons because the states are discrete, and I can fill them. Now, if I add damping, it's another question, but I can think of this, all the phonons here, because this is just a harmonic chain, they're all particles, okay? Now, if I look at the harmonic oscillator, below, I mean, if I'm in a region where a frequency where there's no absorption, we know that the resonance frequency will be renormalized, okay? Because the real part is changed because somewhere there is some absorption, some imaginary part. So, so now I have a new harmonic oscillator with a new frequency that's renormalized, and this is a particle. But that particle contains all the other ones here, if you want, because the frequency has a new value. And the reason it has new value is because there are all these other particles that are virtual because they don't cause any dissipation. That's what we call virtual. Okay. So I'm already very late, so I'll come back to this next time.
Okay, thank you.
Okay.
See you next time.
Okay. If you have questions, you can stay. I'll stop the recording, but you can stay and I can answer questions.
Super, merci. Bonne journée.
Okay.